Time series forecasting uses historical observations collected at regular time intervals to predict future values. This technique finds applications in finance, healthcare, marketing, and more. On the right, you can see an example monthly sales time series chart. Causal inference leverages statistical frameworks to estimate what would have happened had an intervention not occurred, known as the counterfactual. By comparing this hypothetical scenario against observed outcomes, it quantifies the treatment effect. This methodology applies to both observational and randomized experiments and relies on the potential outcomes framework to ensure valid inference. ARIMA stands for auto-regressive integrated moving average, denoted ARIMA of P, D, Q. Here, P is the autoregressive order, D is the differencing degree for stationarity, and Q is the moving average order. The AR part captures dependence on past observations, the I part removes trends through differencing, and the MA part smooths errors from prior forecasts. The autoregressive component models the current value as a linear combination of its past values and a random error. In an AR of order 1, the current observation depends on the immediately preceding value scaled by phi plus random noise. The integrated component, or I, means differencing. We subtract the previous observation from the current one to remove trends and seasonality, which helps achieve stationarity. If one difference is not enough, we can difference again. Second-order differencing subtracts the previous first difference from the current first difference. For example, the series 10, 12, 15, 20, 28 yields first differences of 2, 3, 5, and 8 after ignoring the initial undefined value. The moving average component models the current value as a function of past forecast errors. It captures serial correlation in the residuals by weighting previous errors. The parameter Q determines how many lagged errors are included. Here is the MAQ formula. XT equals mu plus the sum of Q lagged error terms each weighted by theta plus the current error. Mu represents the constant mean level around which the series fluctuates. The summation term accumulates the last Q error terms, each multiplied by its coefficient theta I, capturing how past shocks influence the current value. Finally, epsilon t is the new random shock at time t, representing unexplained variations. The ARIMA model order is specified by three parameters, P, D, and Q. Parameter P indicates how many past observations, or lags, are used in the autoregressive component. Parameter D represents the number of differencing operations needed to make the series stationary. Parameter Q determines how many lagged forecast errors are included in the moving average component. Pre-post analysis compares observations before and after an intervention date. We plot the metric over time, mark the intervention, then compare average levels in the pre-period against those in the post-period to assess impact. The autocorrelation function shows a slow decay, indicating autoregressive behavior. The partial autocorrelation cuts off after 2 lags, suggesting an AR model of order 2. If the ACF cuts off after 1 lag while the PAF decays gradually, this indicates a moving average process of order 1. In summary, for AR models, the PAF cuts off after P lags while the ACF tails off. For MA models, the ACF cuts off after Q lags while the PAF tails off. For ARIMA models, both ACF and PAF tail off. The Akaike Information Criterion, AIC, measures how well a model fits the data while penalizing complexity. The Bayesian Information Criterion, BIC, adds a stronger penalty of k log n, which increases with sample size. Here is a side-by-side comparison. AIC uses a penalty of 2k, while BIC uses k log n. Lower values indicate a better model. AIC favors predictive accuracy. BIC is better for finding the true model in large samples. In hybrid forecasting systems, ARIMA models capture the linear components of a time series, while machine learning models account for nonlinear residual patterns. The final forecast is obtained by summing the ARIMA forecast and the ML residual forecast. Causal inference is transforming forecasting. First, it brings cause and effect analysis into time series models. Second, it supports robust policy and business decisions. Third, it leverages specialized methods such as causal ARIMA and difference in differences. Causal ARIMA extends traditional ARIMA by estimating intervention effects when no direct control group is available. Difference in differences compares treated and control groups over time to isolate the causal impact of an intervention. In this simplified example, the gray line is the control trend. The teal line represents the treatment group, which diverges after the intervention at time 3. This divergence is what the difference in differences method quantifies as causal impact. Explainable AI adds transparency to forecasting. ARIMA's clear structure helps build trust and satisfy regulations. ARIMA's auto-regressive, differencing, and moving average parts each map to intuitive steps, making the model transparent. Here is the concise ARIMA notation. A simple time series line and forecast point illustrate how each forecast traces back to ARIMA's components for full interpretability. Automation in time series forecasting streamlines the entire modeling workflow. It automatically ingests data, selects optimal model parameters, generates forecasts, performs diagnostics, and deploys results with minimal human intervention. ARIMA models help forecast organic search traffic trends. Here we show a 12-month history of sessions, plotted as a dark blue line. An ARIMA 212 model chosen by minimizing AIC projects the next 3 months in teal. These forecasts guide SEO strategy and resource planning. Difference in differences is widely used in healthcare to assess policy effects. For example, researchers compare readmission rates before and after new protocols between hospitals that adopt the change and those that do not, and they measure infection rates in regions with and without vaccination campaigns. The core difference in differences formula calculates the difference in outcomes between post and pre-periods for treated and control groups, isolating the intervention effect. This schematic chart shows readmission trends. Before the intervention at time 0, both groups follow parallel paths. Afterwards, the treated hospitals' readmission rates drop significantly, while control hospitals remain nearly constant. In supply chain management, ARIMA models capture demand variability over time, forecast reorder points, and optimize inventory levels. First, we review the key objectives. ARIMA models need the time series to be stationary. Achieving stationarity by differencing can remove long-term trends. ARIMA captures only linear dependencies. Nonlinear patterns require more advanced or hybrid models. Outliers and structural breaks can distort ARIMA estimates, leading to inaccurate forecasts if not properly handled. Standard ARIMA is not designed for multiple seasonal cycles. Seasonal ARIMA extensions are needed for complex seasonality. Choosing the optimal PD and Q parameters involves extensive diagnostics and can be quite complex. Looking ahead, time series forecasting will evolve along 4 major dimensions. Finally, real-time scalable forecasting with dynamic models will become standard practice.